Hi, welcome back to the AP Physics B Summer Assignment Lecture videos. Today's lecture video is about kinematics, in particular uniform motion. So what is motion? It sounds like kind of an obvious question. When is an object moving? When is something described as moving? And again, you have to say, well, with respect to what? If you recall from Mr. Wright's lecture, you remember the gentleman in the car with his coffee. He was driving along with no problem. And he would describe the coffee as not moving. However, Albert Einstein on the side of the road would describe the coffee as moving and probably very fast. So motion is all relative, and it depends on your frame of reference. So keep in mind it's always important to define your frame of reference with some kind of coordinate system. All right, so motion is basically a change in position or location with respect to some arbitrary origin. It's going to happen over some time interval. Could be a very short time interval, could be a very long time interval, but there is some time interval involved. And to describe it again requires a frame of reference. So here's a little video clip app kind of thing that I found to try to talk about this in a very simple way. So we have a little red car, and I'm setting up some markers here to say that, all right, from my origin, I'm going to call this, where's my pen? There it is. I'm going to call this spot here my origin, okay? And I'm going to say that the positive direction for my car is this way to the right, okay? And any motion in the positive direction would be to the right. So this spot here is my zero point, my origin, okay? And at t equals 0, I'm saying that x equals 0. So here we have our first experience with some letters. These letters are variables, and in this case we have the t is our time. T is the symbol we use for time, and time is a scalar, so there's nothing special about how we write that. Then we have x. X is position. X actually, position is a vector quantity, so I mean, we could do that. Well, we could define it that way with our pen. Your textbook will use bold letters or bold print, but you can always put a little arrow over the symbol in order to indicate that it's a vector quantity. So, at any rate, that's my coordinate system, my frame of reference. Those are my units are going to be meters, and we've set up our variables. And there goes the red car. You can see that it's moving at a pretty constant rate. You would probably say that the speed is constant throughout that motion. We would say in physics that it has a constant positive velocity. And the actual value of that velocity is something that we'll be figuring out in just a minute. So the car that we just saw was in a state of uniform motion, meaning that it didn't speed up or slow down once it got going. It did not turn, and therefore it did not undergo an acceleration. We'll talk more about acceleration later. So all I've done here is I've upended my little app, and not for any great reason except to go ahead and show you that even though the car is moving horizontally from left to right, I'm going to go ahead and I'm going to plot its position on the ordinate of my coordinate system here. Remember, the ordinate is the y, what you are referring to as the y-axis, but it's our ordinate. The abscissa is going to represent time. So if I watch that car again, at time 0, again it was at its origin, and then it went ahead and ran straight to the right for about 6 seconds. And I actually timed this earlier, and I found that for the most part, that car starting at 0, every second went about 10 meters. So I'm going to plot that on my graph. All I'm doing is plotting the position of the car at every second. And again, I only know this because I went through and I timed it. All right, so then I would connect the dots. I'm trying to keep that nice straight line. It's not too bad. It's not great. But I can see that that line has a constant slope. Whether I determine the slope with these 2 points here, here and here, or the slope throughout the entire graph, I'm going to get the same value. And just to make sure that we all understand why, remember slope is rise over run. Slope, remember, is m in your algebra equations. So m, or slope, is rise over run. In this case, we've got the ordinate over the abscissa values, the change in the ordinate over the change in the abscissa values. Now what does that mean? In this case, it's our change in position over our time intervals. So if we look first at this little guy here, between 1 and 2 seconds, I have a run of 1 second. I have a rise of 10 meters. So that gives me a slope of 10 meters per second. And that tells me how fast the car is moving across that time interval. If I look at the entire time interval, the car has traveled 60 meters. So the rise is 60 meters. The run is 6 seconds, which is a slope of 10 meters per second. And note the units here, meters per second. Meters per second is a change in position over time. Meters per second is also the SI unit for velocity and also for speed. We're kind of specifically trying to learn about velocity here, so I'm going to try to use the word velocity more than speed. Remember, speed is a scalar. It is the rate at which something's moving. It's how fast. But in this case, we also know what direction the car is moving. It's moving to the right, so we have a velocity here. All right, so back to displacement now. Let's get a formal definition with our variables here. Okay, displacement again is a change in position. Position is actually a vector quantity as well. Okay, you can define an object's position with respect to an origin. So a change in position, since you're just subtracting one position from another, is also a vector quantity. So, and again, we've already said that displacement's a vector quantity. So there's our displacement equation. Velocity. Velocity is our change in position as a function of time. Usually we talk in terms of average velocity in this course. So you could call that v. All right, velocity is going to be represented with a v. Many books will write v average, and again, it's a vector quantity, equals or is defined as delta x. And remember, x is our position, so delta is change in position is displacement, over delta t. T is a time interval, or I'm sorry, t is time, so delta t is change in time or time interval. So we can actually pull that out even further. So we could say this is equal to x minus x naught over t minus t naught. Okay, oops, forgot an arrow there. All right, now instantaneous velocity is a bit more complicated, and it gets into a graphical analysis for us. Let me come back to that in just a minute. One quick other thing about average velocity. Oftentimes you see it described as v bar. All right, v with a bar over it. That's also average velocity. All right, instantaneous velocity is defined as the limit as delta x, or I'm sorry, as delta t. That's a t. As delta t approaches 0 of delta x over delta t. Now, if you haven't learned about limits yet, which you should have been introduced to them at least, a limit has to do with when you're analyzing a function. If you can shrink down this time interval in this particular function where we have delta t as our denominator here, if we shrink that down as we look at a smaller and smaller segment of time, so that the time is approaching 0, the time interval is approaching 0, we're getting closer and closer to what we call an instant in time. And you could say that whatever the change in position is as that delta t approaches 0, that is your velocity at that instant in time. Now, how do you do that? What generally happens is, in simple examples like the one we just had where we had a straight slope, remember we had a slope that was constant, well, we could take any point on that graph and say, well, the velocity is the same all the way through, so our instantaneous velocity is actually the same as our average velocity. However, what's more common is you're going to have graphs that do weird things like this. Not really weird because they're more common than that. And when you have a graph like that, and again, this would be x and this would be t, then you can't really nail that down. You could say, well, you could look at this little time interval in here. Let's see, from here to here, and that's almost a straight line, so you could figure out that slope. But then if you look at the time interval between here and here, that's a very different slope, and that's different from this slope, and these are curvy. So if you wanted to know how fast is this object traveling right here at this point, that you really couldn't do that with our basic definition up here. What you'd actually have to do for the purposes of what we're doing, you'd actually have to draw a line tangent to that, or you could actually make your calculator figure this out for you, and you take the slope of that tangent line, and that's the instantaneous velocity. When you learn more in calculus, you'll find that you can take the derivative of the position vector, and that will give you the instantaneous velocity. But now I've got the three cars together here. Let me go back. There we go. All right, and what I want you to do is watch, in general, which car wins the race, which car comes second, which car comes third. So let's watch that real quickly. Okay, so over the course of this 80-meter race, the blue car won, the red car came in second, and the green car came in third. Everybody should be able to see that. If I plot the displacement of the blue car versus time, and I timed this earlier, I find that the blue car traveled a total of 80 meters in roughly 3.5 seconds. So if I just put a point here at 80 and 3.5, I could connect the 0 with that, and that would give me a representation of the motion of that car. Now, it's not a good representation because we know that car changed its velocity, but we can actually just say, okay, over that whole time period, this would represent the change in position versus time, and that's true. So I could say V average for the blue car is delta x over delta t for the blue car, which was 80 meters over 3.5 seconds. And you can calculate what that would be. I could then look at the red car, which came in second, and I could say, well, V average for the red car is the same 80-meter displacement, same delta x, but the time was different. It was a slower time. So the same 80 meters over, and that one was about, I think it was 5.1 seconds, something 5.2 seconds maybe. And then lastly, the green car, again, to find its average velocity, we have delta x over delta t, same 80 meters, but this time it took about 5.5 seconds. So we can see visually from the graph that the blue car has the steepest slope. Its position time graph has the steepest slope. The green car's position time graph has the least steep slope. So it's pretty obvious if we didn't even watch the race, we could see that the blue car would have won that race. It went the same distance in a shorter amount of time. But again, this is just an average velocity. We didn't really plot out, point for point where that car was at every second. If we had done that, we would definitely not see a straight line, because we could see from the actual little race that the blue car sped up after its initial starting speed. So we'll get back to that in just a minute. Let me go through here. All right, so if we looked at just the first 40 meters of the race and plotted that out, this is what the position time graph would have looked like. So yes, the blue car was still in the lead, and I can tell you that it was the blue car that's still the steepest slope there. But because of the second 40 meters, if we plot the whole thing, in other words, these red lines are the same that we just saw in the previous graph. Here, I'll go back. You can see that. Now these are red. Okay? But if we compare that to, if we compare these, which represent the whole race, to these guys, which represent the first 40 meters only, we can see there's a change in slope. So there was a change in velocity. Now what we haven't done, again, we haven't plotted out second for second what each car was doing. That would give us a lot more information. And that's why we need to learn about acceleration in the next segment.